All right, so we're back to think a little bit more about these connections between energy and equilibrium, between energy and chemical reaction, and how we can use these or leverage thermodynamics to tell us something about chemical reactivity and prediction about whether things would react, things will react. And we were talking last time about the intricate nature or relationship between equilibrium and thermodynamics, and how it turns out that in a stoichiometric reaction, the reaction goes forward because it's trying to get to a point where it has less free energy, where free energy was sort of our catch-all combination of all thermodynamic factors that can tell us something about whether a reaction or a process is spontaneous or non-spontaneous, whether it will occur or whether it will not, generally. And we talked about how equilibrium doesn't get to that completion, that level of completion, because its minimal point for free energy falls somewhere in between reactants and products. So you end up with a mixture of the two of them that's dependent upon the energetics of the reactants and the products. So we can relate these free energy changes or changes in free energy to the equilibrium constant using the expression that's right here on the slide, where the change in free energy is equal to minus RT times the natural log of the equilibrium constant. We know already this is delta G as our change in the free energy. K is the equilibrium constant, T is the temperature, and R is the gas constant. These are all things that we've seen or talked about before in one form or another. Remember, we've used about 3 or 4 different versions of the gas constant at this point. It just sort of depends on what situation, which one you'll use, but the gas constant or the form of it will be back to the 8.314 joules per mole degree K. Temperature, of course, always has to be in Kelvin. And the free energy changes in joule. And we're going to find that that's going to be not problematic, but somewhat problematic. The idea that free energy here is going to be calculated in joules, and sometimes entropy a lot of times will be expressed in terms of joules as opposed to kilojoules, and it won't be a problem, but it won't make our life very much fun, because we're going to have to convert between joules and kilojoules frequently as we go through thermodynamics. All right, so that leads us to, can we calculate an equilibrium constant based solely on a free energy change? And we saw already that a free energy change is minus RT times the natural log of the equilibrium constant. That will be the standard form of the free energy change that we're dealing with here. And so we can just literally start plugging things in. You know me, I like to have on the right a list of things that are going to be like pumped into the expression. R 8.314 joule per mole Kelvin. Temperature has to be in Kelvin. We're at 25 degrees C, and we add 273.15 to that to get 298.15 Kelvin. And remember that because the gas constant, is in joules, we need to have our free energy change in joules as well. So that's going to be 21.4 kilojoule. That's a positive free energy change. And then we have 1 kilojoule is 1,000 joules. So the free energy change is going to be 21,400 joules. All right, and I mean, and a lot of times these are joules per mole, and you're going to see that the mole will go away or cross out. So really this should probably have been kilojoules per mole and this is going to be represented as joules per mole. Sometimes that gets left off, but it's an important thing to think about. So let's just start plugging in. 21,400 joules per mole minus the gas constant 8.314 joule per mole Kelvin. Sorry, my K not so easy to read there. 298.15 Kelvin. And then we have the natural log of the equilibrium constant. Now, the reason why I came back and I said, joule per mole or kilojoule per mole is probably the more appropriate way to express this, is because you're going to see what's going to happen. We know equilibrium constant has no units, so all these units should collapse. So Kelvin on the top here is going to cross out with Kelvin. Joule is going to cross out. Mole is going to cross out, and everything's going to be left with no unit, which is exactly what we want for equilibrium constant. So now let's start making some of these calculations collapse. 21,400 equals minus 2478.82 natural log of K. Again, we're just not worrying a whole lot about significant figures at this point. And I can't tell you how much better it is to do a calculation when you don't worry about sig figs. I know you know that already. If you haven't figured it out, you will have figured it out soon. And I'm guessing you have. I don't know why I said that. I know students don't like to do sig figs. Not fun for us either. So let's go through. We're going to divide both sides by negative 2478.82, and we get minus 8.6331 equals the natural log of K. And again, we're back to that point with logarithms. Like I said, I had to punt on doing a lot of instruction on logarithms, but I did send you a link above. You really ought to take a look at that. It's really quite good. But natural log has a base of 10, so you'd raise 10 to these. You'd use 10 if this were logarithm, but natural log we use something called e, and we're going to raise e to the minus 8.6331, and we're going to raise e to the natural log of K. E to the natural log of anything is just anything, so e to the natural log of K is going to be K. E to the minus 8.6331, that would actually be important to look at that. And I think we might have already done some things with natural log, but I just want you to notice. So if you want to raise e to the something there's an e to the x function here. You have to hit shift natural log. That's right above the natural log, so you can grab that. And so if we want to do 8.6331 negative and wanted to raise e to that power, we just hit shift natural log, and we get equilibrium constant to be 1.781 times 10 to the minus fourth. Okay, so that's it. I mean, that's our equilibrium constant. Now, it'd be nice to think about what that equilibrium constant actually means. So we have an equilibrium constant here that's very small. So would that mean we would have more reactants or more products when we get to equilibrium? I'll let you think about that for a second. And it means we have fewer products. So that means that whenever we have this acid here, formic acid, and it gives up a proton and ends up producing its conjugate base, that not much of it is going to end up in the deprotonated state. Most of it's going to stay like this. It makes complete sense knowing what we know about acids and weak acids in particular, because this is a weak acid. All right, weak acids don't dissociate a whole lot, so fewer products. This makes sense for a weak acid. All right, so if we think about it, we can come back to where we can get to the point where we can conceptually try to understand, okay, how does this relate to the actual chemical system? And for a weak acid, the equilibrium constant should be fairly small. So that's how we get to the point where we can calculate an equilibrium constant based on the thermodynamics. And now we want to talk a little bit about the idea of, spontaneity. And we have seen this already. So this isn't something that's, completely a surprise to you. During the last lecture, we actually talked about this expression where we can combine enthalpy and entropy together to determine what the free energy would be. We know the sign of free energy. If free energy is positive, that was non-spontaneous. And if that has a sign that's negative, we said it was spontaneous. All right. And so we can look at the enthalpy, we can look at the change in entropy, and we can try to determine, whether something will be spontaneous or not, whether a chemical reaction would be expected to move forward based solely on the energetics. So there are two different ways that we'll use that. Number one, we might just look at it through inspection, giving the enthalpy and entropy change, or we can even just be given the sign of the enthalpy and the entropy change, determine if the reaction is spontaneous. Sometimes those will be straight, right out calculations. Other times it will just be you have to visually inspect to try to figure that out. And then next, can we calculate enthalpy and entropy changes from a balanced chemical equation and then determine whether that reaction is spontaneous? And we're going to get to there, but we're first going to think about how we can use that expression or use that relationship between free energy, enthalpy, and entropy to changes to determine whether a reaction will be spontaneous or not. And so here we have this reaction where we've got hydrogen peroxide decomposing to produce water and oxygen. That is the basis for so many great chemical demonstrations, and I likely will do one in the next couple weeks so that you can see that decomposition. One of my favorites is elephant's toothpaste, and I'll have to do that one for you. Maybe I can record a video of me doing elephant's toothpaste in a couple different ways so that you can see it, but it all relies on the decomposition. And so we want to say, okay, if we have hydrogen peroxide sitting around, will it just spontaneously break up into water and oxygen? And I want to think about this in two different ways. Okay, the expression that we're going to use, of course, is the free energy change equals the enthalpy change minus the temperature times the entropy change. And so I just want you to look at this expression. Okay, we know that this is exothermic. The enthalpy change here is negative. So we know that the enthalpy change is negative. It's exothermic. We want delta G to end up being negative. And then we want to determine, okay, how does entropy change? Now this we know how to do, all right? We have hydrogen peroxide here. It's breaking up, and oh my gosh, this is a gas molecule of oxygen. So we have hydrogen peroxide dissolved in solution to produce water as a liquid, all right, and oxygen. And we know that we can predict what an entropy change would be just from looking at a chemical reaction. Generally, entropy will increase if you increase the number of molecules or ions or things that are produced in the reaction. Entropy will increase if that's the case because there are more molecules or more things to spread the energy over. Remember we talked how about conceptually you can think about that in terms of disorder, but in reality it's how can we spread the energy out, and if you can spread the energy out more, that's more favorable. So we would look at this and we'd go from 2 molecules to 3, and one of them is a gas as opposed to these liquid phase species. So gases tend to have more entropy. So we would predict that entropy change would be positive. And you might well be looking at it and saying, Dr. Ramsey, I can look right at the number and see it's positive, but it's important for us to be able to do both of those things. All right? It's important for us to be able to do the calculation, but it's important for us to think about it conceptually. So what would we expect the sign of the free energy change to be if the entropy change is positive, the enthalpy is exothermic, it has a charge of, or a sign of negative, and we know temperatures are always positive. So in this case, we've got a positive number, all right, we've got a negative number minus a positive number, so at every temperature, this reaction would be expected to have a free energy change that's negative. So we would predict that it's going to always be spontaneous. Always be favored, all right, by thermodynamics. Now can we go through and we can we calculate what that free energy change would be to see if our prediction is correct? Now honestly, this is the most straightforward case, because in every case this free energy change should be negative. So if we get something that's positive, we know something's wrong. I like problems where you can sort of figure some of that stuff out on its own. And our free energy change equals our enthalpy change minus temperature times change in entropy. We don't know what our free energy change would be equal to, but we know that our enthalpy is minus 196.1 kilojoules. Then we have a temperature and we have a change in entropy. So remember, this is where I said there are mismatched units for enthalpy changes and for entropy changes. So look, one's kilojoule and one's joule. I'm just going to convert this one to kilojoules, and so you'd get 0.12 plus 0.1257 kilojoules per Kelvin. And then we've got to have our temperature in Kelvin, 25 degrees C plus 273.15 is 298.15 Kelvin. All right, so now we have everything that we need to plug in. Remember, we got to match those units so that we can have kilojoules and kilojoules, or we could have converted this to joules and matched them that way, but it was just easier for me to convert that one to kilojoules before we placed it into the equation. So 298.15 Kelvin. Entropy change is plus 0.1257 joule per Kelvin. Kilojoule per Kelvin. Kelvin crosses out. Now we're going to be left with a free energy change in kilojoules, and so we get the free energy change is minus 196.1 kilojoule minus 37.48 kilojoules, and the free energy change is minus 233.6 kilojoules, which is exactly about where we would expect it to be, right? We said it should be negative. We would predict it would be negative. That negative sign means that this is spontaneous. So we would fully expect that this reaction would occur under all temperatures. All right? So that's how we can use that expression to both predict and calculate whether a reaction will be spontaneous or not. Now, it's not always going to be given that we're going to know the enthalpy and the entropy changes, and this is going to bring us back to something that we would have done in general chemistry, first semester general chemistry class. So let's take a look at how this works. So remember, we said there were two different ways. Number one, given an entropy and enthalpy change, determine whether a reaction is spontaneous. The second is, can we calculate the enthalpy and entropy change from the chemical equation? All right, this is something that you know how to do already, and I'm going to just prove it to you here in a second. Because not always are you going to be given directly that enthalpy and entropy change. You might have to calculate it. And you might say, well, I don't know how to calculate something like that, but it turns out that you do, because you've done this before and you just may not realize it. But we can use, remember we said we could use heats of reaction or heats of formation. This is probably better said heats of formation to calculate enthalpy changes. We had a way that we could do this called Hess's law, but Hess's law doesn't always have to be heat of formation, but this one right here, we can determine the heat of reaction. It's the sum of the number of moles from the balanced chemical equation times the heat of formation for the products minus the sum of the number of moles from the balanced chemical equation times the heat of formation for all the reactants, and you add that all together. And we said we could then calculate an enthalpy change for pretty much any reaction that we want, provided that we have the proper heats of formation. And you can generally find those tabulated in the back of a textbook, or you can search for those for sure. There are lots of tables of those on the internet that you would be able to find. But it turns out that that's not the only thermodynamic term. We can actually do this with entropy changes as well. So entropies have been measured for different compounds. And remember I said that's a difficult thing to do, and indeed it is. But a number of them have been calculated and tabulated. So you'll find in these tables of thermodynamic information, you oftentimes will find entropies as well as enthalpy changes for different substances or different compounds, and we can go through and do the same thing. And what do those tables look like? Well, they look something like this, where we have standard molar entropy values. You can see that they're listed for a number of different compounds. If you're looking in the back of a textbook, you're going to find that it'll probably have heats of formation and things like that right along with it. And so you can use those or get all that information all at the same time. And so you can see there are a number of different compounds here as their entropies, and we can go through and calculate. And I think it's useful to go through that process with you, even though you know how to do it, or have it illustrated that you can do this. And so first of all, I want to try to predict the sign of what the entropy change would be for this reaction. And here we have multiple reactants and their gases. All right, gases, we said, tend to have high entropies. There are multiple different compounds here, 3 different compounds, 1 carbon monoxide and 2 molecules of hydrogen. And we're forming 1 molecule of liquid. So we would expect this to have high entropy and this to have low entropy. So we would expect the change in entropy to be negative. We would expect the entropy to be decreasing. The energy is less spread out here than it would be with these molecules in the gas phase here on the left. So this is not favorable thermodynamically. Things don't want to have decrease in entropy. They want to have an increase in entropy. So they want to have a positively charged delta S. So we can predict now when we get to the end, we have something to sort of hang our hat on. So we said that the entropy change for this particular reaction would be the number of moles times the entropy for the products minus the sum of the number of moles times the entropy for the reactants. And we've got our product and our reactants, so we can just start plugging everything in. So if we were going to do this, it would be for the products first, it would be 1, because there's a 1 in front of that, 1 times the entropy of CH3OH. And that's it. That's our only product. Our reactants, it would be 1 times the entropy for carbon monoxide plus 2 times the entropy for hydrogen. So now all we need to know is what those entropies are, and I just happen to still have that table around. I haven't thrown it in my pile on the floor yet. We can find the entropy for carbon monoxide. We can find the entropy for hydrogen gas. We can find the entropy for methanol. And we can then go and plug those back into that expression. We can solve it and determine what the entropy change will be for this reaction. So the change in entropy will be equal to 1 times the entropy for methanol, 126.8, and that's joule per Kelvin per mole. And that 1 technically has a mole on it, so that's going to cross out, minus 1 times the entropy for carbon monoxide, that's 197.674, and that's going to be joule per Kelvin mole. The mole crosses out, plus 2 times the entropy of hydrogen, 130.684 joule per Kelvin per mole. And again, the mole is going to cross out from the 2. And we're going to be left with joule per Kelvin, which is the unit for entropy. So if we start calculating this, we get 126.8 joule per Kelvin minus, if you calculate all of that together, you get 459.042 joule per Kelvin. And when you tabulate that or calculate that, you get minus 332.24 joule per Kelvin. All right, sign is negative. We predicted the sign of the entropy change to be negative. And so that gives us at least some confidence to say that we've probably done this or done something correctly as we were going through and working on this problem. So we get to the point where that's what our entropy change would be, and so we could then go back and use that in this expression, delta H minus T times delta S. We could then go and use that in that expression to try to calculate what's the free energy change. Is this spontaneous or non-spontaneous? We can do the same thing with enthalpies if we'd like to. And it turns out that that's not the only case, because free energies have been tabulated. All right, so we're back to looking at, okay, we can do the same thing. You can find free energies of formation that are tabulated for different compounds, and you can use those to go back and figure out what the free energy of a reaction would be to determine whether it's spontaneous or not. And so this will allow us to predict whether something is going to be spontaneous or whether it's just not going to happen spontaneously. Is it going to be favored thermodynamically or is it not? That sort of gets us to the end of the thermodynamics section. I mean, we really hit all the high points, and that's about as far as we're going to go on thermodynamics in Chem 110 and 111. I think that that's enough. I know that there's a lot of lecture material for you this week. Probably over a good hour and 10, hour and 15 minutes of lecture. And so literally I'm posting all of this on Monday, and there will be no new lectures on Wednesday for you. I think that will make you happy. And then our quiz is just going to, on Friday, that you'll get next Friday, or on Friday, will be just based on this thermodynamic stuff. So that's thermodynamics for you. Have a great day.